I shall now try and estimate the vibrational frequency. That means how many times the car will go up and down every second if the spring is not designed properly, and or if it's worn out and the car starts shaking after going over a bump. Now, even before estimating an answer, let's just take a moment to think about what kind of value we might expect. Now, if you have ever sat in an old or a poorly made car, right, you would probably have felt the kind of vibration in the car as it drives, and each time it goes over some bumps, you might feel the whole car shaking quite obviously. So we are talking about maybe a few times a second. So this is the kind of vibration we might actually expect. Okay, so let me just say we are expecting maybe the frequency to be a few hertz. Hertz meaning cycles per second. So every second it sort of shakes a few times, and that can get quite uncomfortable if it happens all the time. Now, in order to start our estimates, we have to think about how to make reasonable estimates. So first of all, we need to we need, let's see, to find the frequency we need to know right, we want to find f, so we need to know period, or we need to know omega, the angular frequency. And we know that angular frequency is related to k and m. Right, while we're here, let me just write down one more relation. If you look at this expression for omega and this expression for f, you see that the difference is a 2 pi. So in other words, f can be directly related to omega. You just have to multiply f by 2 pi. As you can see from here, if I multiply this by 2 pi, I get this. So therefore, I have this relation here that that omega is actually equal to 2 pi times f. Now I'm going to write this here as well, just so I know what I need to work out. So in order to find the frequency, therefore we need to estimate k, the spring constant, and m, the mass of the car. So let's think about how we can make reasonable estimates. Let's clear this. To make a reasonable estimate, we start with what we know about. Let's say we start with the mass. Start with the mass of the car. Now, what do we know about the mass of the car? If it is a small car, we might expect that it is probably quite a bit heavier than the driver. But let's start with the people in the car. Let's say there are 4 adults. Okay, let's say there is an adult person driving the car. Now, what is the mass of an adult? Varies a lot. So let's say the average adult would probably be under 100 kilogram. Big adult might be more. So let me say take as an upper estimate or a higher estimate, 100 kilogram for an adult. So we might have maybe an average car might sit 4 adults. So let's say there are 4 adults and the mass is 4 times of that. Okay, so that makes 400 kilogram. But how heavy is the car itself? Probably quite a bit heavier than this. Okay, so that makes already 400 kilogram. So without actually going and search for a value of the car, let me just make a simple estimate at the total of the car plus the people. Right, let me say it is 1,000 kilograms. So that gives us a nice round number, which is a ton. Now it's completely approximate, but it is a simple way, to make estimates, quick estimates, rough, but maybe not too far from the answer, is to think about what is called orders of magnitude. Just make this down. Order of magnitude. Roughly speaking, we can think of order of magnitude as a number that tells us roughly how big something is, just very roughly. And the usual way, not really always clearly defined or explained, but the usual way to think about orders of magnitude of some quantity is to think in terms of multiples of 10. So for example, if I want to look at something, maybe a book or a person or a car, I want to try to imagine roughly what the mass is. Now the easiest, very simple way is to think in terms of multiples of 10. Like I might start from, say, 1 gram, then think about multiples of 10. So 1 gram, 10 grams, 100 grams, and then I go to 1 kilogram, and then I go to 10 kilograms, and then I go to 100 kilograms. Okay, then I go to 1,000 kilograms, go to 10,000 kilograms, and so on. So you get the idea. So it is as if we divide in this all the possible weights into these various categories, these various classes of sizes or magnitudes, if you like, and we roughly choose one that seems reasonable. Right? For example, some of them are quite obviously not reasonable. Like we wouldn't think that the total weight of a car and people is 1 gram. Right? We know 1 gram is very small. Well, assuming that you've seen something that is 1 gram before, maybe like a piece of paper is 1 gram. So if we know something about our own weights, we would know that it wouldn't be 10 kilogram or 1,000 kilogram. It's some tens of kilogram. So maybe a bit closer to 100 kilogram, but not quite. So we can take 100 kilogram as the order of magnitude for the weight of a person. Now for a car, it might be a lot heavier than the 4 adults. Okay, so I don't know, maybe it might even go up to 10,000 kilograms. I have no idea without a proper check, but let me just take it as a rough estimate. Well, the car is not really that much bigger than a person, but there are metals and iron inside that makes it heavy. So I'll just take 10,000 as the 100. I'll just take 1,000 kilogram as the total mass of the car and people. It might be off by a few times, okay? But I just want a rough estimate of the frequency. So let's see how it goes. See if we can get the reasonable answer that we want. Okay, we can always make it more accurate by looking it up. So coming back to this, so now I have an estimate for the mass. All right, so order of magnitude is the way to go if you want to make rough estimates. Now the next thing to do is to think about the spring constant. If I just say spring constant, it's difficult to imagine what value it should take. So the way we can do it is to relate this spring constant to something more familiar. Now, familiar means what we can see, usually like mass or weight, length, and time. These are what we see and feel all the time. So we have to think of, if we know a formula, some formula for the spring constant that relates it to something else, and we do, that would be Hooke's law. Okay. So Hooke's law, right? Okay, so it says that force is equal to spring constant times the extension. Okay. So now we are on to something. You see, the force here would refer to the force on the spring. In this case, it is just the total mass, total weight of the car and the other adults. And we have already decided that 1,000 kilogram is a rough estimate for the total mass. So in other words, we know the weight now, right? We know the weight. Now, so the next thing I need to do is, if I can find this extension, I would then be able to calculate the spring constant. So how could we make a reasonable estimate of this extension? Okay, let's look at the spring again. At first, it's like that. Then when it goes up, it gets compressed to this length. So in this case, it's a compression rather than an extension. So we need to try and imagine how much it gets compressed. Again, we have no idea about how cars are made, and I've never seen a spring in a car before. So we can Google for that, but it still doesn't tell us how much it might be compressed unless we actually look at a real car and measure it. So let's do it this way. Let's start with the spring. Now let's try and imagine what the length of the spring is. Again, using orders of magnitude. Let's try and put it in some categories, like maybe a centimeter, 10 centimeters, a meter, 10 meters, and so on. So there are not that many. Let's try and decide between 1 centimeter and 1 meter. So 1 meter is about the height of a child, or close to the height of a person. Okay. Now, if we have stood next to a small car, we know that we would be slightly taller than a car, and the adult would be slightly taller than a car. So it's unlikely that the spring would be as long as 1 meter, because that would make it maybe as high as the car, or nearly. Okay. Now it's maybe unlikely that it would be just a centimeter. You know how big is a centimeter? It's less than, it's quite a bit shorter than your own finger. All right, maybe just about the thickness of your own finger. So that is a very small thing. Okay, and there's not much to compress and for it to move and absorb the shock. So in between 1 centimeter and 1 meter, we have 10 centimeters is the next order of magnitude. It's the order of magnitude in between 1 and 100 centimeter. So 10 centimeters, okay, that might still be a bit short, okay, but it might be 20 and or so or more. But let me just take it to be 10 centimeters. Okay, if I take this to be about 10 centimeters, then what might be then the possible compression in the spring? Oh, by the way, it might not even be a spring as in this coil thing. There could be other forms of springy materials that can be used in its place. So I shan't go into that. And this might be completely off. But let's just hold our breath and see how this goes. We will learn quite a bit of physics along the way. So this compression, if you have a spring, when you compress it, we might imagine that you won't be able to compress it the whole length as much as 10 centimeters, but maybe a fraction of that. So let me say that let me just make another guess that the compression, the x this time, all right, that will be yeah, this amount, actually, this amount, that's the x, to be fraction of that. So again, the next order of magnitude down is about 1 cm. So I'm just going to take x to be about 1 centimeter. So that's my 1 centimeter. And the f I would have got from the weights, which the mass I've already decided falls within the 1000 kilogram order of magnitude category. So to find the force, I want the weight, which is mg. Now I know that g is 9.81 meters per second squared, but since I'm doing orders of magnitude, very rough calculations like that, rough but still reasonable. All right, that's important. Reasonable is important. I'm going to take this as roughly 10 meters per second squared. So I have 1000 for the mass. The mass is 1000 kilogram, and this has 10, the g, and I have 1 cm for the x. So now I have all the numbers, all right, rough numbers, but I have the numbers for the spring constant. Okay, so we are ready to estimate that. Okay, so f k is f over x. So let's do it. F is mass times g, 1000 times 10, 1000 times 10, and x is 1 centimeter. You need this in SI units. The formula is in SI units. So that's 0.01. Okay, now we can find the number. We're talking about 1, 2, 3, 4, 5, 6 with 6 zeros. This is 10 to the power of 6. And the units will be newtons per meter. So there we are. We have the mass m for the angular frequency, and we have k for the angular frequency. So we are all set now. Let me just copy out the numbers here. So the k is 10 to the power of 6, and the mass is 1000. Now you can see now that we should actually be able to use this formula now to calculate f. So let's do that. First, let me clear this off. Oops. Clear off some space. Okay. Now I want to first find omega, and then I want to find f. So let me start with the omega. Or let me just do it all at one shot. Okay, the f there is equal to omega divided by 2 pi. So omega divided by 2 pi. Now omega is the square root of that. So that's 10 to the power of 6 over 1000. That's 10 to the power of 3. So that's 1000, right? This is 1000. So this is square root of 1000 divided by 2 pi. Okay. Now at this point, we can actually use our calculator to find an answer. But let me just do the whole lot by hand, so you can see that there is this quick way to make estimates, even when you don't have a calculator. So 1000 is really the same as 10 times 10 times 10. Okay, divide by 2 pi. For the 10 times 10, if I take the square root, I just get 10. For the remaining 10, if I take the square root, it is about 3. Right? Because 3 squared is 9. So it's quite close to 10. And pi there is about 3 as well. Pi is actually 3.14. Okay, that's actually, square root of 10 is actually 3.333 and so on. Okay, right. Let's okay. Let me then cancel those two and those, and I have the answer 5 hertz, 5 cycles per second. So that is close enough to the few hertz that I said we would expect right at the start. Okay, close enough for us to have some confidence in the way that I've made the estimates.